Most people think ancient civilizations lived above ground, but across China, engineers were digging kilometers underground, without GPS, without engines, without modern tools. In one case, two teams dug toward each other from opposite ends of an 8-kilometer tunnel. One mistake, and the project would fail. They didn't miss. No laser equipment, no modern surveying tools, just pure geometry and precision. And modern engineers? They still study these techniques today. Here's what nobody tells you. It might look like a simple underground cave. Actually, many of them were underground military highways, industrial drilling systems, and desert water networks. And the disturbing part? Many of these are disappearing, collapsed, filled in, or forgotten every single year. Today, you're going to see exactly how ancient China built 3 underground marvels. By the end, you'll know the step-by-step process, the tools they used, the genius behind it all. I spent the last week breaking down reports so you don't have to. Let's get into it. Number 1. Bozhou underground tunnels. Picture this scenario. You need to move troops across a city. Your enemies can't know. What's your solution? Build 10 kilometers of underground tunnels. That's exactly what happened at Boso. The core 8 kilometers sit 3 to 8 meters below the city surface, and they're still there today. They had T-shaped junctions, parallel lanes 2 to 3.5 meters apart, message passing holes for silent communication, obstacle walls to slow enemies, foxholes for defense, and even booby traps. So how did they build this? Let me break it down. Engineers marked the tunnel route on the ground. They used stakes and rope, simple tools. They calculated the depth, 3 to 8 meters. This was based on soil stability. They likely divided the 10-kilometer route into shorter sections, perhaps on the order of 50 to 100 meters, and planned where to dig vertical shafts. This part is critical. The shafts served 6 functions: worker entry and exit, debris disposal, ventilation for oxygen, alignment references, lighting access, tool storage. Workers dug straight down using hand pickaxes and shovels. No machinery. They removed soil in baskets. Human chain relay. Once they hit the right depth, they reinforced the walls with wooden poles to prevent collapse. Ladders were installed for climbing. They may even have opened small vents along the shafts. Why? To prevent workers from suffocating. This is where the real innovation happened. They used something called the 2-entry convergence strategy. Here's how it worked. They divided the tunnel into sections. Team A started digging from one end. Team B started from the opposite end. Both teams dug toward the middle at the same time. The advantage? This cut construction time in half. But wait, how did they keep both teams aligned? This is the million-dollar question. They used measuring rods above ground. Workers positioned 2 vertical rods above each shaft. They sighted along these rods. If the rods formed a straight line, the teams below knew they were roughly on track. Underground, they lowered a marker stick down each shaft. Workers followed the stick's direction. This prevented crooked tunnels. The excavation teams had small number of workers per shift. They used iron or bronze pickaxes. They scooped debris into baskets. Baskets went up through the shaft via rope. They worked in rotating shifts, probably 4 to 6 hours each. Why? Oxygen concerns. Now here's the scale of this challenge. The 10-kilometer tunnel was roughly 3 meters high and 3 to 5 meters wide. That's 90,000 to 150,000 cubic meters of soil, all removed manually with baskets. They likely used gravity chutes through the shafts. The excavated soil formed large mounds. You could probably still see them today. Ventilation was life or death. Workers deep underground face oxygen depletion. The solution? Multiple shafts allowed air to circulate. Warm air from bodies and torches rose through some shafts. Fresh air came down through others. As teams got closer, the final 10 to 20 meters required careful work. Both teams listened for pickaxe sounds. When they heard the other team, they knew they were close. The final meters were excavated slowly. Too much force could cause collapse. When teams broke through to each other, major achievement. Once the tunnels were complete, they turned them into weapons. T-junctions for rapid movement, parallel lanes for two-way traffic, hidden openings for communication and defense. It was an underground battlefield. By comparison with other large ancient projects, historians estimate a build time of several years with a workforce in the hundreds. 3 to 5 years is a reasonable order of magnitude, though no exact record survives. The tools were simple: pickaxes, shovels, rope, wooden supports, nothing advanced, just used with extraordinary precision. 3 reasons. First, abundant labour. Ancient China could mobilise hundreds of workers. Second, strategic need. Hidden troop movement was worth the effort. Third, geological advantage. The relatively soft alluvial soils there were far easier to cut than solid bedrock. But that's just marvel number 1. The next one, they drilled 1,001 metres deep, with bamboo and iron. Number 2. Sichuan Boreholes. The first manually drilled well passing 1,000 metres wasn't made with engines or. The deepest hole in the world wasn't drilled by oil companies in the 1800s. It was drilled in China in 1835, more than 1 kilometre deep. No engines, no explosives, no steel pipes, just bamboo, iron, and human strength. Imagine ancient Sichuan. Salt wasn't optional. You needed it to preserve food, to survive winters, to trade. But the salt wasn't near the surface. It was trapped deep underground, mixed with brine, far deeper than anything people had ever reached before. So the question was simple and terrifying. How do you drill deeper than 100 metres when you don't have machines? The solution they discovered was brutal, but brilliant. Percussion drilling. They lifted a heavy iron bit, dropped it, rotated it slightly, and dropped it again. Over and over. Each strike shattered a little more rock. Centimetre by centimetre, the hole went deeper. This technique didn't appear overnight. As early as 250 BC, they were digging shallow salt wells. By around 50 AD, they made a critical leap from digging to drilling. And over centuries, they refined it. By the 1700s, wells 300 to 400 metres deep were common. Then, in 1835, they achieved the impossible. The Shanghai well reached 1,001 metres deep, drilled entirely by hand. To do this, they had to solve problems no one had ever faced before. First, height. They built towering drilling rigs, up to 40 metres tall, made almost entirely of bamboo. Why bamboo? Iron corroded in salt water while wood warped and cracked. But bamboo was strong, flexible, and resistant to salt. It became the backbone of the entire system. Second, collapse. As the hole went deeper, the walls wanted to cave in. Their solution was another bamboo innovation. They split bamboo poles, hollowed them out, and stacked them into a casing, sealing it with tung oil and lime. This casing held the walls together and blocked water from flooding the hole. And it worked. Some of these bamboo pipelines were still in use over a century later. Progress was painfully slow. Some days, they advanced only a few centimetres. Workers stood on wooden planks, using their body weight to lift the drill bit. They worked in rotating shifts. Oxygen was limited and mistakes could be fatal. Reaching 1 kilometre deep took years. But then, something unexpected happened. At extreme depths, they struck natural gas. At first, no one knew what it was, but they quickly realised it burned, cleanly and powerfully. So they adapted. They built the world's first natural gas pipelines out of bamboo. They split bamboo lengthwise, sealed it with lime and tung oil, bound it with rope, and laid it end to end. Gas flowed from deep underground straight to surface furnaces. They burned it under evaporation pans to extract salt from brine. One well now produced 2 resources: fuel from gas and salt for trade. Over centuries, Sichuan drilled more than 13,000 wells. They produced an estimated 70 million tonnes of salt. Modern geologists believe the region yielded over 30 billion cubic metres of natural gas, long before the modern energy industry existed. Entire cities were built on this system. China did it in 1835, with bamboo, iron and human ingenuity. And the next marvel might be even more precise. A desert water system so unforgiving that if the slope was off by even a little, entire cities would lose their water supply. Number 3. Karez system. Imagine living in the desert, no rivers, no lakes, summer temperatures above 40 degrees Celsius. If water evaporates on the surface, your city dies. So ancient engineers faced an impossible problem. How do you move water across miles of desert without letting the sun touch it? Their solution was radical. Don't fight the desert above ground. Go under it. They built vast underground water highways, called Karez systems, that quietly carried water from mountain foothills to cities. No pumps, no engines, just gravity and precision. The first challenge was knowing where to dig. Engineers studied snowmelt from the Tian Shan Mountains. They tracked how water seeped underground and identified where the water table could be intercepted naturally. Get this wrong and months of work were wasted. Get it right and water would flow for centuries. Once the route was chosen, work began with vertical shafts. Workers dug straight down, sometimes more than 100 meters deep, using hand tools. These were spaced every 20 to 70 meters along the route. Each shaft served multiple purposes: worker access, ventilation, debris removal, and later maintenance access. Digging these shafts alone could take months, and it was dangerous. Oxygen was limited. Workers rotated in short shifts. Torches were their only light. When water finally appeared at the bottom of the first shaft, they knew they'd hit the source. Only then could the real work begin. Now came the hardest part, connecting all those shafts underground. The tunnel had to slope slightly downward, about 1 meter per kilometre. Too steep? The water would erode the tunnel. Too flat? The water would stagnate and clog with silt. There was almost no margin for error. And remember, this all happened underground, in darkness. This is where ancient ingenuity shines. Above ground, engineers placed simple vertical rods at the tops of 2 shafts. By sighting along these rods, they defined a straight line, the exact direction the underground tunnel needed to follow. Then they lowered a guide stick down into the shaft. That stick became the tunnel's compass. Underground teams dug toward the stick, constantly checking their alignment, slowly, carefully, metre by metre. This method kept tunnels astonishingly straight over long distances. Modern surveys show deviations of only a few centimetres over kilometres. Once alignment was set, horizontal excavation began. Workers crouched in tunnels barely 1 metre wide and 1.5 metres high. They dug with picks, loaded soil into baskets, and hauled it up through the vertical shafts above. As one tunnel reached the next shaft, a breakthrough moment occurred. Then the process repeated, shaft by shaft, section by section. Over time, the underground canal stretched for kilometres. When the final tunnel connected to the oasis, water began to flow, silently, constantly, by gravity alone. No pumps, no fuel, no moving parts, just physics. Once completed, the Karez system barely needed maintenance. The underground route protected water from evaporation. The steady flow prevented sediment buildup. Vertical shafts allowed easy access for repairs. That's why many Karez systems worked for hundreds of years. In the Turpan region alone, over 1,000 systems, more than 5,000 kilometres of underground channels, supplying water to thousands of square kilometres of farmland. Some still function today. This was an amazing precision engineering. Every mistake would have been invisible until the water failed to arrive. And failure didn't mean inconvenience. It meant crops dying, towns collapsing, and entire communities abandoning their homes. Yet again and again, the water flowed. And when you step back, a pattern emerges. Hidden tunnels for armies, kilometre-deep wells for industry, invisible water highways across deserts. These weren't accidents. They weren't brute force projects. They were systems designed with geometry, patience, and a deep understanding of nature. Ancient Chinese engineers didn't rely on machines. They relied on precision and worked with the environment. And that's why these structures lasted. But here's the uncomfortable truth. Many of these underground worlds are disappearing, collapsed by neglect, filled in by modern construction, forgotten because you can't see them from above. In some regions, hundreds have already been lost. Once they're gone, the knowledge goes with them. And that's what makes these marvels so important. They prove that advanced engineering doesn't require advanced technology. It requires careful planning, layered problem solving, and respect for the limits of nature. Modern engineers still study these systems because they're efficient, low-tech, high precision, built to last. So the next time you hear someone say the ancient world was primitive, remember this. Beneath the surface, entire civilizations were solving problems we still struggle with today. If you want more deep dives into lost engineering, hidden systems, and ancient innovation that shaped the modern world, make sure you're subscribed and tell me in the comments which one shocked you the most. I'll see you in the next one.